Hello children, welcome to aimsindia's online classes. In today's video from physics subject, force and laws of motion topic we are going to continue. So in our previous class we learned about inertia children, and mass is the measure of inertia. We learned about concept of force and the relation between force and motion we have discussed. So in today's class we are going to learn about Newton's laws of motion. So Sir Isaac Newton has proposed some laws regarding the motion of a body. They are known as Newton's first law, Newton's second law, and Newton's third law. About these three laws we are going to learn today. So according to Newton, every body continues to be in its state of rest. Suppose if the ball is in rest, it continues to be in the state of rest, or if it is in uniform motion like this ball, it continues to be in uniform motion along the same straight line unless and until it is acted by an external force to change its state. It may be state of rest or it may be state of uniform motion, unless until if it is acted by a force, up to that moment it will be continue in the same state of rest or same state of uniform motion. So to change its state, we have to apply an external force. So Newton's law tells about this thing. So this we have already learned in the concept of inertia. This we have learned already in the concept of inertia. So the Newton's first law is also called as law of inertia. Law of inertia, because the first law describes the intrinsic property inertia of a body. So it is called law of inertia. So if a particle at rest continues to be at rest, or a particle moving with uniform velocity continues to move with uniform velocity, so then the net force acting on it will be zero. Net force acting on it will be zero. We should not tell there is no force when the body is in rest or when the body is in uniform motion. We should not tell there is no force. We have to tell there is no net force. We have to tell there is no net force. Forces may be acting on the body while its state of rest or state of motion is constant. But why it is not able to change its state means because of no net force. This force may be plus 10 newtons, another force may be minus 10 newtons. If we add both, plus 10 minus 10 cancel, overall net force will be 0 newtons. So when the body is under rest or in state of uniform motion, we have to tell no net force is acting on the body, or net force acting on the body is 0. But we should not tell there is no net force. So if there is a net force, which net force? If there is a non-zero net force, the particle will accelerate. The velocity will change and the particle will accelerate. That is about Newton's first law. So Newton's first law describes about inertia, which we have learned already. Let's revise once again. So here it is very easy to push the empty bucket rather than pushing the bucket full of sand. Why means the empty bucket will be having less mass, less inertia. The bucket with sand will be having more mass, more inertia. So more force we have to apply here compared to this empty bucket. So inertia means the inability of a body to change its state by itself without any force. That is called inertia. So mass of a body is the measure of inertia. So Newton's first law is also called as law of inertia. So this Newton's first law of motion explains the concept of force qualitatively. More mass, more inertia, more force we have to apply. Like that, it cannot tell the quantity of force, but it can tell the quality of the force. So Newton's first law explains the force qualitatively, but not quantitatively. So the inability of a body to change its state of rest is called inertia of rest. Actually, in inertia, we have three types. We will discuss in next slide. Suppose here, the giraffe is traveling in a car. Suddenly, the moving car, if any obstacle comes in its way, if it touches the obstacle, the giraffe will bend down. The giraffe will bend down. Why means? Because of the obstacle, the car may stop. But previously, as the giraffe is in motion, after touching the obstacle also, it tries to continue its state of motion. It tries to continue its state of motion. So that's why it will bend forward. And if there is anything, it may get hurted. So that's why the persons traveling in the car asked to wear a seat belt as a precautionary measure. Why means? This thing may happen. Suddenly, if any car, suddenly if the car driver applies brake, so then you may jump forward or you may slightly move forward with the same speed that you may get hurted with the glass of the car or body of the car. So that's why you have to wear a seat belt as a precautionary measure. The damage will be more if you are, especially if you are like a giraffe. If your height is more, then damage will be more to you. So here in inertia we have some types. So the inability of a body to change its state of rest is called inertia of rest. Suppose when a bus suddenly starts, before it starting, you will be at a rest position. If the bus suddenly starts, though the bus is moving forward, but your body tries to stay there only. So that's why there will be a slight fall off backward. So if the bus moves suddenly forwards, you may fall slightly backward to um, keep your state of inertia of rest. So that is called the inability of your body to change its state of rest is called inertia of rest. Or the inability of a body to change its state of motion is called inertia of motion. Suppose a body released from an artificial satellite. Suppose if this body is connected to the planet, this satellite is connected to the planet. So suddenly, if any body drops from the satellite, what does it will do? It tries to move in the same orbit for some time with same speed. Why? Because previously it was in motion. It tries to continue the same motion with the same speed for some time. Why means it don't want to change its state of motion. So that is called inertia of motion. That is called inertia of motion. Or the inability of a body to change its direction of motion by itself is called inertia of direction. Suppose here you can observe the sparks coming out from the grinding stone. The sparks coming out from the grinding stone. In the lower part, when it is touching this iron body, the sparks are coming out. the sparks are coming out. The wheel is touching the iron body which is at the bottom and is going up. When it is touching down, its direction will be along the tangential direction. The direction at the point of contact will be along the tangential direction. The sparkles also tries to move in the same tangential direction without any change. So like this, we have three types in inertia. One is inertia of rest, another one is inertia of motion, another one is inertia of direction. So inertia of rest means if a body is at rest, it continues to be at rest unless some external force is applied on it. That is inertia of rest. Examples: when a train at rest starts moving suddenly, so passengers in the compartment fall backward because they don't want to change their state of rest. Or when a carpet is beaten with a stick, when you take a stick and when you beat a carpet, the carpet may fly off, the carpet may fly, but the dust particles, they will fall down there only. Because they don't want to move along with the carpet. They want to stay in the same rest position. So that's why the dust particles gets detached from the carpet and starts falling downwards. Or when a bullet is fired into a glass pane, we have a glass pane, a bullet is fired from the gun, bullet is fired. So what it will do? It will make a hole in the glass pane and it will pierces through the hole and went in and goes to that side without breaking the entire glass pane into pieces. Only in that part it will make a hole and penetrates through the glass pane. So these are all examples of inertia of rest. Next, inertia of motion. So when a body is in uniform motion, it will continue to remain in its uniform motion. That is, it resists any change in its state of motion because of one property that is called inertia of motion. The examples are when a person jumps out of a moving bus, as the bus is moving, or while traveling in city bus, you might have observed so many passengers, they will get down the bus, get down the moving bus. How they will get down? They will get down and they will run in the same direction. After getting down, after jumping down, they will run forward in the same direction of the bus for some time. Otherwise, what happens if they suddenly jumps and stops? Previously, their body was in motion. Their body continues to move in motion. And if they suddenly stops, their body will fall forward. So that's why, to avoid that, after getting down, after jumping down, they will run in the direction of bus for some time. Or a train moving with a uniform speed. And if a ball is thrown upwards inside the train by a passenger, the train will be moving. Here one person is sitting. He throws a ball. As the train is moving, the person will come forward. And if you keep the hand, the ball will comes to his hand again. Why means, as we are throwing the ball from the running train, the ball also will possess the same velocity of the train. It travels for some time with the same velocity of the train, and it will comes to the hand, because the ball continues the inertia of motion. That's why it is coming to our hand. Next, inertia of direction. So a body moving in certain direction cannot change its direction without any force being applied on it. So it is the property due which body maintains its sense of direction. Direction does not change. It is called inertia of direction. So when we travel by a motor car, if it takes a sharp turn at a very high speed, along with the car, suppose if we take inward turn, so our body will slightly bend in one direction. Our body slightly bend in one direction. Why means, we want to change the direction of the car, but our body still wants to be in the same direction. So that's why slight bending of our body we can observe in that case. So we tend to get thrown to one side. We feel that our body is thrown to one side. Why means, this is because of inertia of direction. Previously, we are going in straight line. If we suddenly takes a turn, our body, the car may takes a turn, but our body continues to be travel in straight line. So that's why we feel that we are thrown out of the car. Means, when an unbalanced force is applied to change the direction of motion of motor car, we slip to one side of the seat due to inertia of direction. So these are the three types of inertia. Children, next children, let's learn about linear momentum. So a body of mass m, if it is moving with velocity v, then the product of this mass and velocity mv is called momentum, denoted by the symbol p, capital P. So it is called linear momentum. If it is moving in a straight line, the momentum observed in this case is linear momentum. So its symbol is P. So linear momentum is a vector, means we can represent it as P bar is a vector. It points in the direction of velocity vector. The SI unit of linear momentum is mass unit is kg, velocity unit is meter per second, kg meter per second or kg meter s to the power of -1. And its dimensional formula is kg means mass m, meter means length L, second means time t power -1. This is the dimensional formula. If the net force acting on a particle is 0, means if the net force is 0 means its velocity will be constant. If the velocity is constant, indirectly mass of a body is always constant. So indirectly linear momentum of a body also will be constant. If there is no net force, or if the net force is 0, then the linear momentum will be constant. One minute. Next one, linear, Newton's second law. So according to Newton's second law of motion, the rate of change of linear momentum means change of momentum with respect to time. Whenever we consider with respect to time, it is defined as rate of change of linear momentum. The rate of change of linear momentum of a particle is equal to the net force on the particle, acting on the particle. So net force F. So net force F is defined as rate of change of momentum. Rate of change of momentum means change of momentum by time taken or time interval. So change of momentum means if the initial velocity is u, mass into velocity mu is the initial momentum. If final velocity is v, mv is the final momentum. Change of momentum means mv minus mu. M we can take common, m into v minus u by time taken t. But v minus u by t means change of velocity by time is already defined as acceleration. So in that we can take ma. In the place of this we can take a. So F equal to ma. This is the definition of force which we have derived from Newton's second law of motion with the help of linear momentum concept. So Newton's second law defines force and it tells about force quantitatively. It tells the value of the force which we can calculate with the help of formula ma or m into v minus u by t. So here the direction of net force will be in the direction of change in momentum, but need not be in the direction of change of velocity. So this force direction depends on momentum direction, but not on velocity direction. So the SI unit of force is Newton, CGS unit is dyne, and its dimensional formula is mass. Mass dimensional formula is m. Acceleration dimensional formula is L1 t power minus 2. So m1 L power t minus 2 is the dimensional formula for force. And the relation between SI unit and CGS unit is 1 Newton equal to 10 power 5 dyne or 1 dyne equal to 10 power minus 5 Newtons. Or it is also defined as kg, its unit also defined as kg meter per second square in SI system, centimeter gram per second square in CGS system. This kg meter per second square is called Newton, centimeter gram per second square is called dyne. 1 Newton equal to 10 power 5 dyne or 1 dyne equal to 10 power minus 5 Newtons. So here children, the net force acting on this boy depends on rate of change of momentum, and the net force acting on the second boy also depends on rate of change of momentum. See here, mass is different, here mass is different. So here change of velocity is more, here change of velocity is less. So here like that, the Newton's second law defines force quantitatively. Next, let's learn about weight. So the gravitational force acting on a body towards the center of Earth is called weight of body. So any body standing on the Earth, if any body is on the Earth, it will be attracted towards its center by the Earth, and this gravitational force acting on the body towards the center of the Earth is called weight of the body. So all the bodies on the Earth, if they have weight, means it is only because of the gravitational force. So the formula is W equals to mc, mass into acceleration due to gravity. Weight equal to mass of the body into acceleration due to gravity. So the weight of a body is measured by a spring balance. The weight of a body changes with its location in a gravitational field, but the mass of the body does not change. So weight means mg, mass of the body always constant, does not changes, but weight of the body changes from place to place as g value changes from place to place. And next children, we have about impulse. So impulse means force acting for short duration of time which vary with time. It is called impulsive force. The force acting in very short duration of time or which will vary with time is called impulsive force. Impulsive force means the collision between two billiards balls. They will hit and immediately one ball will go this side, one ball will go this side. Means for a very short period of time, they will be in contact with each other. That is called impulse. Or a nail driven into a wall by a hammer. So a nail, if you want to fix it into the wall, by hammer. So by a hammer, when we touch it with the hammer, at that particular moment, it will be having impulse. And the SI unit of impulse is Newton second, NS, and dimensional formula is M1, L1, T minus 1. So impulsive force, impulse also one kind of force only. Impulsive force acts in the direction of change of momentum produced by the force. So force, impulse, change in momentum, change in velocity, acceleration, these are all the quantities, main 5 quantities, which always lie in the same direction. They are interdependable on one another. So when the impulse also calculated with the formula force into time, means with how much force for how much time it is in contact with the other object. That short span of time and that short span of force occurred in that short span of time is called impulse. Its symbol is J and its formula is force into time. So if the ball stays for long time, so there will be less force, indirectly proportional. If it stays for less time, more force will be there. If it stays for more time, less force will be there. Next one, we have Newton's third law. Newton's third law tells that for every action, there is always an equal and opposite reaction. So action equal to minus reaction. That is about Newton's third law. So this action reaction always will be equal in magnitude but opposite in direction. So while walking, when we press the grass on the ground with our foot, and after that we went away. But when we touch the surface, the foot is keeping pressure on the or applying force on the earth. This is action which works on the surface. The surface pushes the leg with same force in the opposite direction. This is reaction force acting on the foot. So action force acts on the surface. Reaction force acts on the foot. So both the forces are both the action reaction, okay, both the forces, both the action reaction forces are acting on the different bodies. So that's why, though they are equal, they do not cancel with each other, because if they are equal and act in opposite direction, one will be plus 10, another will be minus 10. They can be cancelled with one another, 0 newtons. Like that we may calculate. But force is acting on, action is acting on surface, reaction is acting on this foot. So that's why they do not get cancelled. So they always occur in pairs. In a situation, one action is there means immediately accompanying it, one reaction will be there. So they always occur simultaneously, one after other, immediately one after other, without any time gap. There is no time lag between action and reaction. So will be very small gap will be there, which we cannot measure. So we can neglect that easily. So from Newton's third law, we can also define what is the law of conservation of linear momentum. That also we can derive. So Newton's third law is not applicable to pseudo forces. Pseudo forces. Suppose pseudo forces means, suppose if you take the example of a washing machine, or any rotating object, if one in rotating wheel, one object is moving in the rotating wheel. So on the object, what forces will work? Why it is moving in the fixed place means, one force will be pulling it towards the center, one force will be pulling it outward the center, which balances with one another. So that's why the object will be moving in fixed path. So this pulling inside force will be real force, but pulling away, that force is pseudo force. That force is imaginary force. For these kind of forces, Newton's third law is not applicable. So while firing a bomb from a cannon, the force on the ball will be taken as action, and the cannon and the wheel, the cannon attached to the wheel, from this place it will be moving towards this place. That will be the reaction force acted on the cannon. Next one, limitations of Newton's laws of motion. So there are some limitations for this Newton's laws of motion, children. These laws are applicable only for speeds which are very less than speed of light. Speed of light is 3 lakhs 10 power 8, 3 into 10 power 8 meter per second, or 3 lakh kilometer per second. But it is applicable for speeds very less than speed of light. That is one limitation. And these laws are not applicable in the domain of atoms, molecules, subatomic particles. Inside that atomic particles, these laws we cannot apply. Or when there is strong gravitational field, at that time also we cannot apply these laws. Or when particles interact with each other by means of a force field, like gravitational field, magnetic field, electrostatic field, if they are affected by the field forces, so then in that case Newton's third law is not applicable. And Newton's law is also not applicable for very small acceleration, like a less than 10 power minus 10 meter per second square. For these small values of accelerations, the Newton's laws are not applicable. Okay, children, that is about Newton's laws, children. So that's all for today. Thank you for watching our video. Please subscribe our channel and press the bell icon for receiving latest updates. You can visit our website, children, www.aimstoday.in, for information regarding online classes, quizzes, worksheets, activities, English classes, coding skills. Thank you, children. Have a good day.